Yeah, so a few quick announcements. You probably saw the announcement, hopefully from your email. I don't know why the spacing, Blackboard formatting, not good. So we're going to start heat transfer and phases of matter this week. I don't know. I'm trying to remember. I think I'll probably go into next week on this module, but I don't know. I can't remember the pacing because last semester I did this module half synchronously, half asynchronously. So there were online videos to watch, and I think it goes a little faster when I do it that way. Anyway, I put a link in here to the module 8. Section, and there's a PowerPoint that has a bunch of figures from most of these are from chapter 4. Some of them I got off the internet, and one set of figures I made myself. I normally draw it out, so I'll probably draw it out, but it looks nice. And I went to all that work last semester to make it, so I'm like, I don't feel like deleting it, so I left it in there. Let's see, key terms. Oh, let's just look at this outline here. This is all of chapter 4 except for section 4.5. So you don't have to worry about section 4.5. I can't even remember. I have to look at the textbook to see. No, there it is. Yeah, section 4.5, I can't remember what it is, but look at that. I have the textbook loose leaf set up here. Phase change, that's right. I don't remember if we even, oh yeah, 4.5 is thermodynamics. Yeah. We don't even cover that. Next. Okay. And then there's applying the concept questions. Again, your homework assignment is right out of these questions, which are in your textbook, and the answers are even given too, but it's a good practice exercise. Again, the homework is intended to be a fairly easy grade for you. Just to read do the reading and then answer the questions. And that's why I give you the unlimited attempts, so you can just sort of use it as a learning tool. There is some supplemental video. I forgot, if you downloaded this last week as a Word document, I forgot to upload or update this. This should only be supplemental videos. So there are some supplemental videos. This is mainly for when we talk about evaporation. I thought these 3 videos are pretty good at giving you a feel for what that means. One thing I do want to point out, I want to go a little backwards here right now, because I found some articles the other day and I added them to the EM, electromagnetic energy. So in module 7, and again, these are more of interest, right? This is probably very much something that you guys see, where if you're trying to be on Wi-Fi, what is the old, is it 2.4 gigahertz? I can't remember. The old 2 gigahertz band. So there's 2 Wi-Fi bands now. There's 2 gigahertz and 5 gigahertz. And microwave ovens are typically on the 2.4 gigahertz. So a lot of times, if you're on an older Wi-Fi, you'll find that you'll get interference with the microwave because they're operating at the same frequency, right? We talked about this on the electromagnetic spectrum. Frequency, and you know what? So if you click this article, it's not that long of a read, but one thing that was interesting is, let's see, where is it? Oh yeah, back in like the 40s, oh here it is, 1947. So almost the 50s. They designated the 2.4 gigahertz band as an unlicensed spectrum, specifically for microwave ovens. And that's why when products like wireless phones, walkie-talkies, right, and then now Wi-Fi, when products were being made for the house, baby monitors, things like that. They would use the 2.4 gigahertz band because it was specifically an unlicensed spectrum, right? It was not something that you needed to have, the FCC set aside specific spectrum for you. So you could just make any electronic device. And so so obviously you've got all these electronic devices in that spectrum now, and they interfere with each other. And one of the big ones is the microwave oven and the Wi-Fi, right? Because a microwave oven is not perfect. It does leak microwaves, and it's not dangerous because it's not the amount it's leaking is not a huge amount of power, right? So this addresses that Wi-Fi cannot cook you, right? So Wi-Fi uses the same frequency, but it doesn't. Your Wi-Fi router is sending that signal out, broadly distributed, and it's a fairly low power. The microwave is using that frequency, but it's putting out a lot more power, and it's focusing that energy in a small little container, right? Yeah, so this is kind of an interesting article about that. And then similarly, you probably heard all the conspiracies around 5G. This is 5G happens to be in the spectrum of about, well, let me open this first. I want to find the spectrum. Let me go out. I have a reference sheet for the next test that shows the whole spectrum on it. Is that it? Yeah. There it is. So 2.4 gigahertz, right? You guys hopefully remember a gigahertz is 10 to the 9th, right? So you're looking at somewhere in this range here. So, the microwave range is a fairly broad range, right? And so 2.4 gigahertz is somewhere in here. Well, it's a log scale, so it's going to be somewhere around there. And then 5G uses, let's see, what does it use? 5G radio waves. So 5G radio waves, I want to say they're like 5G. I want to say they're like 20 to 30 gigahertz. Oops. Hold on. There it is. 20 to 30 gigahertz. So kind of in this, in this range here. That it depends on who's doing the 5G. Like Verizon has its own frequencies, and so Sprint, I'm sure, has their own frequencies. And anyway, the point is here that this is a review of, or this is an announcement saying that they've done not just one but two reviews of experimental studies on low millimeter waves. And remember, we discussed 5G, or sorry, not 5G, radio waves, microwave, all this stuff in the low spectrum here. This is all non-ionizing, right? Anything below UV is non-ionizing. So these waves will tend to pass through you. And yeah, I mean, microwaves are gonna, a certain spectrum of microwaves, the 2.4 particularly, are good at being absorbed by your body. But again, you can stand by your Wi-Fi router and not be cooked. So that energy is just being sort of dissipated to you. It's not, I guess you could block your Wi-Fi with your body. The same thing with the 5G, right? The 5G is going to be in this range, same range. It's non-ionizing. It's not causing any chemical changes to your body. And in fact, it's good that they do these studies, right? Because they want to make sure that, are there any significant effects to these RF towers that we're putting up, these radio towers? Do they have enough energy to cause problems? And what they're finding is, yeah, that there's none, right? There's let's see, we recommend, where's the finding? In conclusion, a review of all studies provided no substantiated evidence. So pretty much no evidence that low-level radio waves like those in the 5G network are hazardous to human health. So this is the the scientific consensus so far is still that 5G radio waves are not going to kill everyone, or I don't know. There was some weird thing about causing COVID, and it's like, well, that doesn't even make sense because COVID's caused by a virus. How do radio waves cause a virus? That was never really clear. But anyway, I thought I'd link those two articles. So those are linked under the EM energy. Let's see. All right, so let's go to module 8 now. I'll just actually switch to the document camera here. We'll start doing notes. We're going to talk about heat and temperature in this module. And this is pretty much, like I said, most of chapter 4 except for section 4-5. So let's just start by defining a few terms here. Before we even talk about temperature, I want to talk about thermal energy. So let's talk about thermal energy. So thermal energy, right? This is kind of going towards, we talk about heating something, right, or cooling something, and that's associated with an object's thermal energy. Oh wait, am I recording this? Yes, I am. Good. So thermal energy is an internal energy that is, this is actually too high of a stack of papers. This is weird. My hand is like hanging off of it. Internal energy that is exchanged with the outside world. Exchanged through radiant and mechanical energy. This is an R. One more comment here, I guess. Everything has thermal energy. And there's a difference between thermal energy and temperature. Now that's a comma, although they are related. So thermal energy, internal energy, everything has thermal energy. And we're going to talk about, when we talk about like heat transfer, how that energy is exchanged in the outside world, right? So you could add thermal energy to something, or you can take away thermal energy from something, right? And thermal energy is not temperature. However, they are related, right? And let's talk about temperature now. So temperature is related to the speed of the particles, speed of the particles that make up an object and heat energy is possessed by all particles so temperature related to the speed of the particles that make up an object, right? So every object has molecules or atoms that are making it up, and the temperature is related to the speed of those particles. Every one of those particles contains or possesses heat energy, and that's what causes it to move. So for the same temperature of a given substance, the heat energy depends on mass. There's another definition of temperature that's a little more thermodynamic related, but it basically relates to, speed of the particles, right, is the kinetic energy of the particles, right? So we remember from our energy, our work and energy, or our study of work and energy, that objects in motion, right, have kinetic energy. Well, the particles that make up anything, right, any material, right, you and me, those particles have a certain amount of kinetic energy to them, right, vibrational energy, and temperature is a measure of that. A temperature is a measure of the average, basically, kinetic energy of particles, right, in an object. Now, for a given substance, right, depending on how much you have, right, you can have two objects of the same temperature, right, but the total amount of heat energy depends on the mass, right? So if I have a cup of boiling water versus a pot of boiling water, they both might be at the same temperature, right, 100 degrees C, but there's more energy in that pot of boiling water than there is in, say, the small teacup of boiling water, right? Because I've got more of it, more stuff. And we'll talk about that in a little more detail later. But first I want to go through the temperature scale. And let's talk about the units of temperature. Units. Oops. Now I'll underline. So we'll talk about three common scales and a fourth that maybe you've heard of, but you probably doesn't really get used very often, particularly in the day-to-day stuff that most people deal with. So the first one is going to be Fahrenheit. I know some of you are out there cheering for Celsius or centigrade, but we'll get to Celsius in a bit. So let's talk about Fahrenheit first. Fahrenheit. And this was developed in 1724 by Daniel Gabriel Fahrenheit. He was a German physicist I should have capitalized German. German physicist who invented the mercury thermometer. Oh, you know what? Let me put a little in parentheses here. This was in 1714. So the actual thermometer was invented in 1714. The scale, you know, I'm sure he had some kind of I don't know that it took him 20 or 10 years to develop a scale, but you know, I'm sure he was fooling around with different ideas and trying out different things. But he invented the mercury thermometer in 1714, and then the scale, the Fahrenheit scale, came out in 1724. I think I can. I don't know if I can fit Celsius, but I can start Celsius. This was invented by Anders Celsius. In what year? 1742. So almost 20 years after the Fahrenheit scale. So he was a Swedish astronomer. Oh, Swedish. Not a Swedish chef, Swedish astronomer. The scale is based on 100 degrees centigrade. So notice, right, centigrade. So centi, 100 graduations is basically where that comes from. And is more compatible, with the base 10 format of SI. Right, which is the metric, all the metric units. So Celsius, that's Celsius. We'll go into more detail about when we start talking about how to convert between them. We'll talk about more detail on that. But let me talk about the other two scales. The next common scale. So I'm sure all of you have heard of Fahrenheit and Celsius, right? Especially living in the area that we do. Even outside of school, right? You may have turned on a radio station and you happen to get one from, you know, from Canada, and they're reporting the temperature in Celsius, and they're like, "Oh, it's 27." And you're like, "What? 27? What are you talking about? It's beautiful weather." Oh yeah, Celsius. Let's look at the temperature scales. Continued here. This is just my numbering system. The third scale is Kelvin. And this was devised by Lord William Kelvin in 1854. So look, Fahrenheit, Celsius, these were developed by by physicists and astronomers, but this guy's a lord, so he devised it. 1854. And what's so special about this? Well, this is also called the absolute temperature scale. Absolute zero. Let me write out zero. Or zero. I'm going to put a slash through this. It's not okay. It's 0 Kelvin. This is the lowest possible temperature. Let's see. Oh yeah. Kelvin predicted that 0 degrees Kelvin would equate to minus 273.15 degrees Celsius. At this temperature, all heat has been removed and all atomic and molecular motion stops or has stopped. Let's put has stopped. So Kelvin actually, one of the incentives of doing this was, it's probably covered in your thermodynamics section, but it had to do with things like trying to figure out thermodynamically what, how much energy you could get out of things. And he developed this absolute scale because you need to have an absolute scale in thermodynamics. It's a different subject that I teach, but just without going into too many details, there are a lot of relationships in thermodynamics that depend on having or knowing the absolute temperature. And the absolute temperature is a direct reflection of the total amount of energy, because at 0 degrees Kelvin, right, 0 on the scale, there's no energy left in the object, which is different for Celsius and Fahrenheit, right? At 0 degrees Celsius, well, that's based on water, freezing point of water. There's still more energy that can be removed from ice, right? It just happens to be, like, you can still get colder than 0 degrees C. You can still take energy away. So that's the Kelvin scale. And then D is the ranking scale. This is the fourth scale. I wish I could have invented something this easily. So this was proposed by William John how do you spell his last name? McCorn, M-A-C-Q-U-O-R-N. William John McCorn ranking. So everyone gets their name on a scale. In 1859. So this is similar to the Kelvin scale, in that it is an absolute temperature scale. Oh, absolute. So zero ranking, this is a zero, is absolute zero. And this is also equivalent to, let me write this out. So zero ranking is equal to minus 459.67 degrees Fahrenheit. So this is what I'm saying. This guy had like one of the easiest ways to get his name on something. Everyone did all the work already. Fahrenheit was invented, Celsius was invented, Kelvin came along and did all this work to develop an absolute scale. And this guy's like, hey, you know what? We could do that with Fahrenheit too. And he just used the conversion factor. He's like, hey, you know what? Why don't we do this for Fahrenheit? Why didn't I think of that? Everyone else is probably like, what? I could have had my name on a temperature scale if I had just suggested this. Let me see. I'm going to open the PowerPoint here. So give me a minute to, I'll open this file here. I'll come back to the notes. I'm sure some of you are still writing this down. So, all right. So that's ranking. One thing that you tend not to see is a degree symbol when you're using Kelvin or ranking. It's just sort of a typical typical nomenclature. Is like you write degree sign F, degree sign C. You don't usually use degree sign R, degree sign K. I'm not actually sure why that convention got it started, but let me just put a note here. Let's see slides for temperature scales. And I can't remember what slides they are, so I'll put them in after we cover them. It's like 1 and 2, I think. Oh yeah, just 1 and 2. These are the 3 scales, right? Fahrenheit, Celsius, Kelvin. And I just want to point out, you probably all know, right? Let's start with the Celsius scale. You probably know that 0 degrees C and 100 degrees C correspond to freezing point of water and boiling point of water, right? The Fahrenheit scale, 0 degrees F is way down here. So it's actually 32 degrees Fahrenheit is the freezing point of water and 212 is the boiling point of water. Again, you're probably familiar with these two. And this one, a lot of people don't really think about the 212 Fahrenheit. So you typically do a lot in school with Celsius, and then obviously, you know, just from day to day weather, 32 degrees is freezing point of water. You don't have very many 212 Fahrenheit days around on Earth. So, so we don't tend to see this number. And then the Kelvin scale comes along, and they decide, you know, we're going to talk about an absolute scale. So the point at which you eliminate or remove all energy from something, right? Like you can still go below the freezing point of water. You can continue to cool things down. For example, liquid nitrogen and liquid oxygen, those are taking the air, right, around us and taking energy out. In fact, this is Praxair's entire business model. If you've ever heard of like Praxair, or now they're Linde, they basically take air from the environment and they put in a lot of electrical work to take energy out of that air and cool it down to very, very low temperatures so that they can liquefy it. And then they get liquid oxygen, liquid nitrogen, liquid argon, and they can separate those by their boiling points because they have different boiling points at really low temperatures. But if you took all the energy out of these things, right, at some point everything becomes a solid without, where down to the molecular level, there's no movement, right? You've taken out all the energy you could possibly take out of something by bringing it down to 0 Kelvin, or on the Celsius and Fahrenheit scales, minus 273 or minus 459 Celsius or Fahrenheit. Yeah, 273 Kelvin, commonly used for 0 degrees, well, 0 degrees C, and 373 Kelvin for boiling point of water. This shows them all in the same. This includes the Rankine scale. Remember the guy that got the really easy job? These are all thermometers at different temperatures, but you can see it gives you sort of an idea. You know, boiling water up here. I don't know, this Finnish sauna does not sound nice to me. Human body temperature is about 37 C, 98.6 Fahrenheit. These are the absolute temperatures. Room temperature, right, 21, almost 70 degrees Fahrenheit. Freezing point, and then absolute 0.
Excuse me.
Yep.
I have a question. It's not related to all of this, but so why do we need all of this for what is the difference? We can
why
just
do we need these scales?
Yeah, we just can pick one, and for all people is gonna be only one.
No, it's irrelevant. I mean, it's a relevant question. I could tell you that it's because everyone wanted their name on a temperature scale. No, it's well, think about this, right? A lot of it depends on what you're dealing with, and I don't know. Like most of the world uses Celsius, right, for day-to-day activity, right? And that's a fairly intuitive scale for, you know, freezing point and boiling point. Fahrenheit, there's really not much, you know, Fahrenheit's one of those scales that, you know, was invented. It was based on, you know, some testing done with mercury, and it's not really, you know, it's not really intuitive to something we worry about every day, right? Like, what's 0 Fahrenheit correspond to? I don't even know. I'm not even sure. I can't even remember what 0 Fahrenheit was referenced to. So in that respect, right? I think most people or most countries have moved to or are even moving towards Celsius. Now, the absolute scales are important. well, at least the Kelvin one. Again, if everyone used Celsius, the Kelvin scale would be still important because that relates to absolute energy, right? And there's a lot of engineering and science calculations that are being done, a lot of engineering calculations that are done that require you to have some kind of, it's just easier to work in an absolute temperature scale. It's more easy to manage the numbers. It gives you a better relative sense of things than flip-flopping over a negative to positive, vice versa. And then you have to use absolute temperature scales in certain things, like when we do calculations for chemical kinetics, right? So how fast chemical reactions progress. There's certain rate equations that are developed, and they only work with absolute values. You get constants for these equations, and you have to use absolute values for these, because that reaction can take place anywhere, right? It can take place at maybe it won't take place, but typically reactions cover a wider range. So you can be below zero. And just in terms of ease of manipulation and generating data and plotting it, it's much easier to work with an absolute temperature scale. Now, I have no idea, to your point about why can't we all use Celsius, I don't know. I mean, there's a lot of history with the Fahrenheit and Rankine scale. It's like anything. If you go out to work in industry, particularly as an engineer, you'll start to look things up, and so many different things have been done on so many different pieces of equipment or over a certain amount of time that, a lot of times you might look in a data book and a company's got some data from like 30 years ago, and it's all in Fahrenheit or it's all in Rankine, right? Or, it's metric system is fairly new compared to a lot of the stuff we've been doing for, the past 100 years. And don't forget, the countries that developed a lot of the technology back in the 1800s were countries like, Britain and the United States, well, England, United Kingdom, UK and the United States, right? Where they were using imperial systems like Fahrenheit or like feet, right? And so a lot of the legacy calculations and a lot of the legacy information is still in those older units, even up until, I mean, I don't even know when the U.S. has never switched officially. Yeah, I mean, still to this day, engineers use both sets of Celsius and Fahrenheit. So I don't know if that answers your question, but hopefully it gives you some insight into what different utility. Now, what's interesting too is the Fahrenheit scale actually gives you better resolution between the freezing point and boiling point of water. In terms of if you just have a scale marked off to degrees F versus degrees C, just because 1 degree F is smaller than a degree C. Oh, I'm not going to get to let me give you some conversion factors and then we'll wrap it up here. I talked too much about the old days. Let's look at conversion factors. Conversion factors for temperature. I'll write these out and then we'll start with this next time when we do some of the problems. So if you want to go from degrees F to degrees C, right? We're looking for the temperature in Celsius. So we take the temperature in Fahrenheit and we subtract 32 first. Notice this equation. This confuses people all the time. You need to subtract the 32 from the temperature in Fahrenheit first. That's in parentheses. Did you guys learn that? You learned it. You remember PEMDAS. It's an order of operation. PEMDAS. DOS. This stands for parentheses, exponents, multiplication, division, addition, subtraction. Those are the order of operations you typically do math in, right? You look at the stuff in parentheses first, you do that. Then you do exponents if you have them, then multiplication, division. Now the addition and subtraction here, this addition or this subtraction is in the parentheses, right? So you actually do that first. If you want to go from degrees C to degrees Fahrenheit, right, that's going to be the temperature in Fahrenheit is equal to, you basically take this equation and rearrange it. So now we're going to have 9/5 times the temperature in Celsius plus 32. This also is equal to, these are equivalent. I'll put a double-headed arrow here. 1.8 TC plus 32. Right, that's what the 9/5 is, the 1.8. So this is telling you for every, oops, ooh, that's an F, TF. Sorry. Did I write this correctly? I did, yes. Every degrees Fahrenheit is 1.8 degrees C plus 32. Right, that's your correlation, your relationship. If you want to go from Fahrenheit to Rankine, we've got the temperature in Rankine, just temperature in Fahrenheit plus, in this class, we're just going to use 460. And then the same thing for Celsius and Kelvin. I shouldn't have put a degree here. Let's see, your degree or your temperature in Kelvin is equal to temperature in Celsius plus, in this class, again, we're going to use 273. I think I mentioned it before, the more exact conversion is 0.15 over here. But, you know, for the intents and purposes of this class, we don't need to worry about that. Let me give you both conversions. You can go to Fahrenheit by taking Rankine minus 460, right? This is just going, if you know Fahrenheit, you can get Rankine. If you know Rankine, you can get Fahrenheit. And same thing for Kelvin. We can write the temperature in Celsius as temperature in Kelvin minus 273, right? So this is just algebra going between these two. I'll write this in red. So in this class, round to the nearest whole degree for, hold on, let me turn my alarm off. Significant figures. So when we report an answer at the end, we'll just round to the nearest degree. I'll start off with some examples next time. So go ahead and print those worksheets out, or just download them and have them available. We'll do these next time. If you want to try doing some of the conversions yourself, go ahead and do that, and then we'll continue this on Wednesday.
All right, thank you so